Evaluate the following sums, showing your reasoning in each case. Okay, before we even start, the formulas that we are given in the formula booklet is a sum of, this is of r squared. This is 1/6 n, brackets n plus 1, 2n plus 1. Okay, we are also given this one, and a sum of r equals 1 of r cubed, which equals 1/4 n squared over and n plus 1. Okay. However, what we are not given, this one here, r equals 1 of r, and this is 1/2 n brackets n plus 1. So this is the only one you've got to remember. It's essentially just half the number you want and the next number on the sequence. So let's use this to work this out. So it's from 20 to 1, 4r minus 2. Okay, we have to break this up into two ones. We've got to break up the 4r part, and we have to break up the minus 2 part. Now the 4r, I'm actually going to take the 4 out, because it's e to the r, which is the formula we got, which is the formula we should know. So that's going to be 1/2 times 20 times 21. Okay, and then all of this I'm going to times it by 4, because that's 4. This one is minus 2. You just got to think all I've got is minus 2 20 times, so it's just going to be minus 2 times 20. Type all this into your calculator, which is 4 times 1/2 times 20 times 21 minus 2 times 20, which equals 800. That's good. For B, we've got 45 r equals 11 of 5r. Okay, so what this is going to be, it's going to be 1 to 45, 5r, and I've taken the 5 out, and then we're going to have to subtract it from 10 of 5r. And the reason why we're subtracting it from 10 and not 11 is because this includes 11, and if we subtract it from 11, 11 would be taken away. So we've got to use that formula again. So it's 5 we've taken out. So 5 half times 45 times 46 minus 5, because take the 5 out, times 1/2 times 10 times 11. Again, put all that into your calculator. So 5 1/2 times 45 times 46 minus 5 times 1/2 times 10 times 11. Those brackets. $4,900. Right, for C, or 16 to 1 of r squared plus 1. Okay, so I'm going to have to break this up into r squared and 1 of 1. Okay, r squared is a formula that we have been given, which will be in your formula booklet, but it's 1/6 n, which is going to be 16, times n plus 1, which is 17, times 2, 16 plus 1, and then we have to add 16 times 1, because that's the second part of this. Again, substitute it onto your calculator. So 1/6 times 16 times 16 times 17 times the bracket 2 times 16 plus 1, 1496, and then you realise you've got to plus 16, so plus 16, which is 1512. And the last one, which is this one here, which is the sum of 14 to 1 of r brackets r squared plus 1. Okay, you've got to expand this bracket. R times r squared is r cubed plus r. So we're going to have to Okay, so to do this, we've got to use a formula that we know, which is going to be the R1, which is half times 14 times 15. Okay, and the R cubed one, which is a quarter times n, which is 14 squared, and 14 plus 1 squared. I'll type all that into my calculator. So I've got a quarter times 14 squared times 14 minus 1 squared plus a half times 14 times 15. I get 8. And the answer is 11130. Find an expression for the sum of 6r minus 3 in between numbers of 1 and n plus 1. Give your answer in the form of an squared plus bn plus c. Right, 6r, I'm going to do 6 lots of the sum of r from numbers of 1 to n plus 1. The minus 3, I'm just going to think of it as just minus 3 lots of n plus 1. Right, this is your hardest one to work out. So what I've got to do is normally half times the last number times the next number. Okay, if we expand this, and my brackets there become n plus n squared plus 3n plus 2. Okay, I'm going to have times this all by half. So let's do it properly. Half. I'm actually going to include my 6's again. And I don't actually need double brackets, but it's just a way to explain it. Expand it for half. N squared over 2 plus 3n over 2 plus 1. All of this then has to be multiplied by 6. 6 divided by 2 is 3, so this becomes 3n squared. 6 times 3 over 2 is actually 9, and 6 times 1 is 6. Okay, don't forget this one here. Let's expand that, which also gives me 3n minus 3n minus 3. We collect our like terms, so it's going to be 3n squared. 9 minus 3 is positive 6n. 6 minus 3 is positive 3. Right, hence find the smallest integer n, such as the sum of 6r minus 3 between the numbers of 1 and n plus 1 has to be greater than 1050. We worked out from the previous question that this becomes 3n squared plus 6n plus 3. The only thing we have to do now is make sure that this is greater than 1050, and we just have to solve. So minus 1050 from both sides, to make it 3n squared plus 6n. It's my calculator. 3 minus 1050 minus 1047. Now I always check to see if this can be factorised. I'll be honest, I can't. So you can complete the square, but I'm going to go for a formula, which is minus b plus or minus square root of b squared minus 4ac. All of this over 2a. Let's see what I've got. So I've got minus 6 plus or minus the square root of minus 6 squared minus 4 times 3 times negative 1047. All of this over 2 times and a was 3. I'm just going to type this all into my calculator. So I've got, it was minus 6. Let's do the positive value first, see what happens. The square root of, remember to put all your negatives in brackets, minus 6 squared minus 4 times 3 times 1047 divided by 2 times 3. Which gives me minus 1 plus 5 root 14, or 17, sorry am I working out here, 17.7082. I'm just going to flip the signs, just so I've got something else to work out, and I can always ignore an answer in my working out if need be. So if I put the minus in, I get minus 19.708. Now obviously I've got a sequence, so it can't be the minus number, so it has to be the positive number. The question did ask me about an integer, so 17.7 isn't correct, so my actual answer has to be 18. Right, show that the sequence 3r squared plus 3r plus 1 between numbers of 1 and n minus 1, made it big so you can see it, equals n cubed minus 1. Right, so there's 3 parts of this one we need to deal with. I'll do 3r squared, I'm going to deal with 3r, and I'm going to deal with the plus 1. Okay, I'm going to split my page up because these can get confusing. Right, so 3r squared, I'm going to break it up to be the sum of 3 r squared. Right, you are given this formula here, which is going to be 1/6 of n bracket n plus 1, 2n plus 1, and I'm just going to put in square brackets. I'm going to put my 3 here because sometimes I can forget about this number. Let's substitute our top value, which was n minus 1, sorry, from the question. So I've got 1/6 of n minus 1. N minus 1 plus 1, which leaves me with n. This one here, 2n plus 1, so which should still be in brackets. 2 lots of n minus 1 is actually just going to be 2n minus 2, and then plus 1. Okay. And again, times it all by 3. I'm going to expand these 2 brackets in the middle first. So I've got a 6th n squared minus n. And this one here just becomes 2n minus 1. This one here, let's do these proper brackets. N squared times 2n is 2n squared. N squared times minus 1 is minus 1n squared. Minus n times 2n is minus 2n squared. Minus n times minus 1 is positive n. I'll put all this in brackets. I'm just going to times these together, just because I can. 3/6 will make it a half. Now on my final bit is expanded. Half times 2n squared is n squared. These two go together to make 3n squared. I'm going to halve it, so 3/2 n squared. And there's a negative sign, and plus 2, so it's going to be plus a half n. I've just realised this should actually be a cubed, and that should be a cubed as well. Because it's n squared times 2n, which is 2n cubed. Right, so we're going to leave that, and then we're going to focus on the next bit, which is a 3r. So it's going to be 3 again, 3 lots of the sum of r. And remember, r is the one that you have to know, okay, which is a half n plus 1. Okay, we've got 3 lots of them. So it's 3 lots of a half n is n minus 1. And when you n minus 1 and n plus 1, that just leaves that as n. Let's expand this. Let's do brackets first. N times n is n squared minus n. I'm going to times this like I did last time to make it 3 halves. And I'm going to expand this one here out to make it, I'm just doing right at the bottom so it's on the lines, 3 halves n squared minus 3 halves n. Okay, and then I've got my so we're going to have to times this 1 times n minus 1, because we still like doing 1 n minus 1 times, which just nicely expands to be n minus 1. Okay, and now because I've done it in the table, I've got all my lines right there, and all my line working out is nice and good. So let's see. So I've got n cubed minus 3 halves n squared plus a half n, and we'll use the next bit, plus 3 halves n squared minus 3 halves n plus n minus 1. Let's go through our powers. N cubed, nothing's happened to that, so it stays the same. Okay, and then I've got 3n squared. Anything else n squared? Oh, plus 3n squared. Nothing else, so they cancel out. Okay, I'm just going to put a box around them, so I know I've already identified them as cancelled out. Just the ends on its own. I've got a positive half, and a minus 3 halves, and a positive 1. Half plus 1 is 3 halves, so they also cancel out. So now I've identified them as cancelling out, and my minus 1 stays where it is, so it's just minus 1. The quartic equation 4x to the power 4 minus 7x cubed minus x squared plus 10x minus 5 have the roots alpha, beta, gamma, delta. Without solving the equation, find all the above. And what I like to do is I like to write down all the, and there's always a trick. I don't care what type, so minus b over a. And that's always going to be the individual ones on their own. And because there's 4 roots, it's going to be 4 of them. So alpha plus beta plus gamma plus delta. and then this is C over A, and that's when they combine together. So it's going to be alpha and beta, alpha and gamma, alpha and delta. I've done all the alphas, so it's beta and gamma plus beta and delta. I've done betas, and I've just got gamma and delta. Good, and then A, B, C, D, so it's going to be minus D because it's flipped over A. So that's the 1s, that's the 2s, it's got to be the 3s, which is alpha, beta, gamma, plus alpha, beta, delta, good, plus alpha, gamma, delta, and I've got beta, gamma, delta. I'm going to do E over A, and there's no minus, and that's 3, so it's got to be the 4s, which is the alpha, beta, gamma, and delta, and there's no other situation I can do from that. So it's always good to write these down first. Now if we go into the question, first one is alpha, beta, delta, alpha, gamma, delta, beta, gamma, delta, and if we look, that's already one of these which we actually wrote down, which is the minus D over A. Okay. Minus D over A. So we go back to our question. A, B, C, D. So it's going to be 10 over, and A is 4. So it's going to be minus 10 quarters. Okay, which is going to be 5 halves. The next one was alpha, beta, gamma, delta. So in the question, alpha, beta, gamma, delta, which is our last one, which is E over A. E happens to be minus 5. So this one here is going to be E over A. It's going to be minus 5 over 4. Okay. And our last one is a little bit more complicated. Because I don't know any of these roots at the moment, I'm just going to try and just add them together like I normally would do, so I need to make the denominators the same. But in this instance, I'm just going to cross multiply. So then my denominator becomes alpha, beta, gamma, delta, okay, which is good. When I cross multiply, this becomes beta, gamma, delta, because I will have two alphas, but they cancel out. Denominator becomes alpha, gamma, delta. And the next one becomes alpha, beta, delta. And my last one is going to be alpha, beta, gamma. You should notice the numerator, we actually know because it's one of the identities that we did before, and our denominator, we should know because it's one of our identities, but the way the question was structured, it's actually part A and part B. So part A happened to be minus 5 halves, part B happened to be minus 5 quarters. I like to think of this as you're doing your GCSE. So keep flip change, keep the first one, flip the second one, change your sign. These minus 5s cancel out to be 1. 4 over 2 cancel out to be 2. So this is 2 over 1, and my answer is 2.
Right, bit of a nasty question. The cubic equation 3x cubed plus 6x squared minus 2x minus 1 equals 0 has the roots alpha, beta, gamma, where alpha plus beta plus gamma equals minus 2, and alpha, gamma, beta, gamma equals minus 2/3, and alpha times beta times gamma is a third. We're normally told to work this out, but it's happy it's not done it. The cubic equation w cubed plus bw squared minus 15w minus q equals 0 has roots 3a plus 1, so 3 alpha plus 1, 3 beta plus 1, and 3 gamma plus 1. Find the integers of p and q. Right, so I'm still going to use the same equations that I always use, which is the sum of the singulars. For my second equation, I'm not going to do it for the first because it's already done for me, is these three added together, which is 3a plus 1, 3 beta plus 1, and 3 gamma plus 1. Okay? And this is going to equal to minus b over a. The sum of 2, which is going to be 3a plus 1 times 3b plus 1. And then it's going to be plus 3a plus 1 plus 3 gamma. So plus 1. And the third one I've done is the plus 3 beta, alright, plus 1 times 3 gamma plus 1. Okay, this has got to be equal c over a. Okay, And let's do the third one, which is the sum of all three of them, which is alpha, beta, gamma. So that's got to be 3a plus 1, because that's the alpha in that one, and 3 beta plus 1, and 3 gamma plus 1. And that's got to equal AB minus D over A. Let's see if this helps us. A, B, C, D. Well, B is minus P, so I'm going to change that to minus P. Minus 15 is C, which might help us out. And D happens to be Q. I'm going to focus on the first one. So if I actually add these together, I get 3 alpha plus 3 beta plus 3 gamma plus 3 equals minus P over A. Oh, sorry, actually no, A is 1, so it's just minus P. If I factorise this, I actually get 3 lots of alpha plus beta plus gamma plus 3. Now, alpha, beta, gamma was actually given to us in the question. If we look up, here it is. Alpha plus beta plus gamma is minus 2. So I can change this to 3 times minus 2 plus 3 must equal my negative P. Okay, 3 times 2 is minus 6, plus 3 is minus 3, so minus 3 equals minus P. So P has to equal 3. Worked out what P is. Now I'm just going to move on to the Q. Out of all this horrible mess, I've got one equation here that actually has Q. And it gets a lot worse because I now have to try and expand this and see if anything nice happens. So I'm going to get another piece of paper. So let's expand the first bit. 3a times 3b is 9 alpha beta. 3a times 1 is plus 3 alpha. So I keep on A. Good. 1 times 3 beta is plus 3 beta. 1 times 1 is 1, plus 1. I haven't done the first bit. 3b plus 1. Now I've got to expand this again. Be careful because there's a lot of terms. 9 alpha beta times 3 gamma is 27 alpha beta gamma. But we know what alpha beta gamma is, but we'll do that in a minute. 9 alpha beta times 1 is just 9 alpha beta. Done right now. 3 alpha. 3 alpha times 3 gamma is 9 alpha gamma. 3 alpha times 1 is 3 alpha. Now to 3 beta. 3 beta times 3 gamma is 9 beta gamma. 3 beta times 1 is just 3 beta. And let's do the 1. I've got plus 3 gamma plus 1. Okay, and this might seem a little bit horrible, but as I said, alpha beta gamma was in the question. So if you've got the question paper back down here, it told me that alpha beta gamma was a third. So I can change this to be 27 times a third. 27 times a third is 9, so that's 9, which is good. I've got my plus 1 here, so I'm just going to put a plus 1. I don't have to deal with that anymore. Now I've got the 2 terms, or 3 lots of 2 terms, so I could consider that as 9. Alpha beta plus alpha gamma plus beta gamma. Okay, I'm putting boxes around these, otherwise I might try and use these again. I know alpha beta plus alpha gamma plus beta gamma is back in my question, which is here. So this is really 9 lots. So this is really minus 2/3. So that's really 9 lots of minus 2/3. 9 times minus 2/3, which is 6. So a bit minus 6. And here I've got 3 alpha, 3 beta, 3 gamma, which I could think of it as 3 lots of alpha plus beta plus gamma. Again, my question, alpha plus beta plus gamma is in minus 2. So that's 3 lots of minus 2, which is minus 6 again. So I've got 9 plus 1 minus 6 minus 6, which is minus 2. You may have forgotten what these all equal, which is Q. So minus 2 equals Q. But I remember this is actually minus Q, so it's minus 2 equals Q, Q equals 2. The cubic equation 27x cubed minus 54x squared plus 9x plus 10 equals 0 has the roots alpha, alpha minus 1, alpha minus 2. Find the value of alpha. Right, so these are your normal roots, which you normally call alpha, beta, gamma. So just for the sake of it, I'm going to put alpha does equal alpha. Beta is going to equal alpha minus 1. And gamma is going to equal alpha minus 2. you have the same equations we normally do, which is sum of your singulars is going to be minus b over a. The sum of both two of them is going to be alpha beta, which is abc over a, and minus d over a. It's going to be the sum of all three of them. Now we've actually got numbers we can sub into these, so these aren't unknowns, these are all whole numbers. It doesn't really matter which one you do, but let's do the sum of singulars, so I'm going to have to add them together. Alpha plus alpha plus alpha is 3 lots of alpha, minus 1 minus 2 is minus 3, so that's this, and I know it's going to be minus b over a, b, so it's minus 54, but it's minus 54, which will make it a positive 54 over a is 27. This gets even easier because 54 over 27 is actually 2. So we're 3 lots of fact minus 3 equals 2. Now let's solve it. Plus 3 plus 3. And 3 lots of alpha must equal 5. So alpha's got to equal 5/3. Right, show that the sum of 4r minus 5, starting at 1, ends at n squared, must equal n squared brackets 2n squared and minus 3. Okay, so it's going to be the sum of r equals 1, n squared, 4r minus 5. I like to always split these up into these component terms. This one here I'm going to deal with 4r, and this one here I'm going to deal with my negative 5. Okay, my 4r is 4 lots of the sum between 1 and n squared of just r. Because that's just r, you're not given this formula, you've got to remember it. And that's one which is half times n, which in this case is n squared. And then it's times n plus 1, because n squared is n, so it's going to be n squared plus 1. Okay, and I've got this 4 times. I'm just going to expand the brackets. I'm going to expand these two first to make it 2. I'm going to expand the right hand side, so it's n squared times n squared, which is n to the power of 4. And then I'm doing n squared plus 1, which is plus n squared. I'm going to expand this bracket again, just to give me 2n to the power of 4 plus 2n squared. Okay. Now I've done all this, I've got to consider my right hand side. It's minus 5, but here's n squared, so this is just minus 5n squared. I'll bring that down to my equation, minus 5n squared. I've got n squares and n squares that I need to put together. Minus 5 plus 2 is minus 3n squared. And I say this is 2n to the power of 4. If we remind ourselves of the question, it was this one here. They look similar, but this one here is obviously factored n squared out, which I can do. So I'm going to factorise n squared out, and I'm going to call that 2n squared, because n squared times 2n squared is 2n4, minus 3, which is perfect. Hence prove that there is no positive integer of n that satisfies the sum of 4n minus 5 in between 1 and n squared, and that's got to equal the sum of 25r cubed from 1 to n. Okay, this one here, it's already like sorted out for me there, so I'm going to deal with that later. So let's do the sum of 25r cubed, which is 25 lots of r cubed from 1 to n. R cubed are actually given in your formula booklet, which is a quarter n squared n plus 1. All of that squared, and there's 25 lots of it. Okay, that's going to equal the previous question, which is that, which was n squared 2n squared minus 3. This double bracket I don't like. I'm just going to make it 25 quarters n squared bracket n plus 1 squared equals n squared 2n squared minus 3. Now it might be tempting to expand all your brackets, and you can expand all your brackets to try and solve them, but n squared's always tried to be a bit naughty, and I've got one on both sides, so I'm going to divide both sides by n squared. Okay, and I'm just going to put that there, because n squared is equal to 0, because that's what happens when you divide by that. And I just got to expand this really, so n plus 1 squared is n squared plus 2n plus 1. And this is going to equal 2n squared minus 3. I can't deal with quarters, they annoy me, so I'm going to times it all by 4, which gets rid of that there. So I've got 25 n squared plus 2n plus 1, which equals 8n squared minus 12. Let's expand this, 25n squared plus 50n plus 25 equals 8n squared minus 12. Let's move this all over to the other side. You might want to do it in 2 stages, but I don't want to. So I'm minus 8n squared from both sides and add 12 to both sides. Okay, so 25 minus 8, I'm typing in my calculator, is 17. So we've got 17n squared plus 50n, and 25 plus 12 is 37 equals 0. So I still want to prove that there is going to be an answer to this, but I know there isn't, so I'm going to use my quadratic formula, but I'm just going to use my discriminant, which is b squared minus 4ac. Okay, and I'm expecting this really to be a negative answer. So let's do it. So I've got 50 squared minus 4 times 17 times 37. Be 50 squared minus 4 times 17 times 37, which is minus 16. So I have to say, so you can't have a square root of 17, so 16, minus 16. So you're going to say that like no real solutions. So I failed in proving that there was a real solution. So I've actually proved what the question is, where it says that there's no positive integer.